what did you get? A bag and a flashlight? Yep. A certificate of appreciation, I believe. Yes, I. There we go. All right. Well, welcome everyone to this afternoon's SME Stamping and Dies Technical Group monthly meeting. So far, we've been chatting between ourselves, myself and Brianne and Brian Roebuck. I see that we've recently been joined by Natalie Lowell, who is staff at SME, and our regular monthly participant Sam Welty has come, and we've just been catching up a little bit. Some of the folks that we were hoping were going to be attending today's meeting have recently sent us email saying that they were running a little bit behind or had other appointments. So I am recording today's meeting, and today's meeting will be posted hopefully shortly after the close of the meeting, as long as my meeting recording works the way that I wanted it to. So welcome everyone, and welcome to today's meeting. Hi, Natalie. Yep, I can barely take the heat. It's really killing me. I'm just kidding. I'm being completely facetious. I'm in Detroit. I braved the 0 degree Fahrenheit weather today to make my way into the office. There is some training going on. I believe at our folks are running it up at Oakland University for Autoform. Um, that's one of our adjunct or annex facilities when we're running especially large training classes. Um, yeah, right. Because there was that guy from Grand Rapids that you had sent his contact information to us, right? Oh, super duper. Glad to hear it. All right. Well, I just wanted to go ahead and kick off today's meeting with the welcome, and as usual, remind people who our advisors are, and also do a quick kind of a roll call, if you will. So today we have, in addition to the usual suspects, we have Natalie and we have Sam. Sam has been joining us almost, what, about almost a year and a half, Sam, you've been coming to our meetings? Yeah, you will, if you keep paying attention like that, we might sneak you in and try to try to con you into becoming one of our advisors. Um, yeah, it's not as bad as we make it sound, but just don't leave. Okay, we won't do it, Sam. Yeah, my name's Eric Com. I am the co-chair of the Stamping and Dies technical group within the forming and fabricating community. My co-chair is Brianne Roebuck, who you've heard talking in the background. Her father, Brian, is an advisor, as well as Dean Phillips. Um, and we are the folks who try to, on a regular basis, make sure that meetings happen within the forming and fabricating community, specifically talking about stamping and dies. As far as calendar of upcoming events, a couple things that I heard about on my radar. Um, on March 26th and 27th in Troy, Michigan, a company called Grundig, who is a metalworking, metal forming supplier to the automotive industry, is having what they call their Grundig Academy Hot Stamping Forum. And so this hot stamping forum that they're hosting in Troy, Michigan is in conjunction with General Motors and the General Motors supplier community, as well as Grundig Academy, my employer's Autoform Engineering, and a couple other hot stamping suppliers, and they're going to have a 2-day forum that is going to have some educational technical talks on the first day of the forum. And on the second day of the forum, we're actually going to have what we're calling circle training, which is kind of short course, 1 hour actual training being built into this typical seminar event. So it's not going to be just a day of seminars and talking heads and death by PowerPoint, but we are in fact going to be doing some training. And on my part, I know that we're going to be doing some hands-on training with hot stamping simulation software. So if any of you are in Troy, Michigan on March 27th, 26th, or 27th, you can find out more about the Grundig Academy hot stamping forum that's hosted there. Also coming up in May, I know that our friends over at the Precision Metal Forming Association will be having a die design and simulation software experience. That is a 1.5 day, not quite an expo, I guess I'll call it a conference or seminar. And at that conference or seminar in Rosemont, Illinois, they are going to have several uh, die design vendors and simulation software vendors, along with our customers, giving case studies on how we're using die design and software simulation to improve overall stamping efficiency and effectiveness. And in the summer, which is hard to imagine, but in the summer, June 1st through the 4th, IDDRG, that's the International Deep Draw Research Group, will be having their annual meeting in Paris, France. I don't know if any of us are game to go to that, but if you are, in fact, a person who likes to participate in those global events, the International Deep Draw Research Group will be having their annual conference in Paris, France. And normally at those conferences, there will be technical presentations from academia, from industry, regarding things such as springback, stamping variation. Hot stamping is a hot topic right now. Alternative materials like aluminum, tooling design, die design, automation design. Pretty much running the gamut of interesting and needful topics of discussion regarding deep drawing or sheet metal forming. Uh, Anybody else know of any upcoming events that are relevant to the forming and fabricating industry coming up? Yep. Well, I wouldn't necessarily say I'm just I mean, sure, if I have the links for registration or for more info for those events, I wouldn't say that the this community or this tech group is necessarily supporting them. I just know that they're relevant to people who are members of our community. So if they didn't know about them, now they can know about them. So sure, I will put the links up. I will post the links when I post the meeting minutes. How's that sound? Okay, thank you. I thought for sure you were going to use that as an opportunity to remind us that FabTech Canada is coming up. Well, I don't know anything about. I actually don't know anything about FabTech Canada. That's why I didn't mention it. I have not been paying attention to FabTech Canada, so I'm not really fully up to snuff on even when it is. So FabTech Canada is out there someplace. I suppose if we Googled it, that it will be happening sometime. I believe it is this first quarter of 2014. Yeah. Okay. See, there we go. So nice little plug in there for the FabTech Canada. That's coming up on the 18th through the 20th of March, and that will be at the Toronto Conference Congress Center. Okay, I can hear Brianne and Brian again. So you guys, your audio seems to be working. At least we can hear you. Okay. Any other upcoming events that folks know about or I've heard about, so that we can make sure that we're up to date and knowing what kind of things are happening inside the metal forming industry. Anything else? Hi, Doug. Welcome back. Aerodef in SoCal. Which design? Pacific Design. And that's just what all disciplines regarding design, or oh, pretty cool. And you're going to be attending? Super, super. You'll have to let us know anything cool or interesting that you find out there. That's Is it okay if I ask you for a homework assignment like that, Doug? Well, that's the thing is that if you can if you see three or four things that are remarkable enough that you it piques more curiosity out of you and you want to have a few more questions answered, or if you see something and you're not sure if it's common or everyday, or if you think it's, uh, it seems extraordinary to you and you wonder, gee, how many people else know about that? Why don't we talk about that next month? Because maybe we find that something you see there is something we don't hear about. In Middle America, right here in the Rust Belt, sometimes what we think is everyday business is stuff that seems, uh, outlandish to folks who are working in aerospace and etc. And of course, the aerospace everyday business and out there on the West Coast, um, some of us would think is totally alien. So absolutely, whatever you see, find a couple things of interest and tell us more about it when you come back. Right? That's kind of a sorry. cool. See, community building is working already. All right, thank you very much. All right, so upcoming events, we have a couple things happening here in the Rust Belt. The Hot Stamping Academy, the PMA Die Design Simulation Experience, FabTech Canada, and then out in SoCal, we got Pacific Design and AeroDef happening shortly. And in the Great White North, FabTech Canada, in just over a month from now. And way far away in June, we have the International Deep Drawn Research Group. So plenty of things to go on, and hopefully stuff to learn and things to share with the rest of our members of community. So thank you very much, everyone. All right. Other things to talk about as far as administrivia and kicking off the meeting. Just again, reminding everybody the calendar of upcoming meetings. The meeting schedule is going to follow the same rotation that we've followed for the past few years. So it's going to be that second Wednesday of each month. We're going to target as our regular meeting day. So every month, just remember that the second Wednesday, we're going to be trying to have a meeting. And that meeting is typically at 1 p.m. Eastern, whatever is the typical time zone at that time. So Eastern time, right? So currently, I believe we are in Eastern Standard Time. That'll always be the 1 p.m. local time for the Eastern time zone. And one of the things that Brianna and I discussed and will be trying out this year, which is a little bit different, is I tried to establish what I might call a editorial calendar. And in doing so, what we did is we came up with kind of a regular rotation of topical items that we'll discuss each month, and just to give ourselves these general ideas or themes. So in the January meeting, for those of you who were here, you might remember that Brianne led us in a discussion just talking about some terminology, different methodologies for the use of dies. When people talk about stamping or people talk about dies, we brought up all sorts of alternative terms, alternative uses, and definitions for the word dies, right? So that was kind of a fundamentals discussion that we had, and I thought a very fruitful discussion because it got us thinking a little bit outside of what each one of us might have as our own individual definition of what is stamping or what is in a die. I also want to, for February, we're having a design and kind of engineering theme. In March, we'll be having a materials theme, and in April, we will have a broad topic within forming and fabricating. So we're going to go outside of what we typically think of as pure stamping and dies discussion and reach into out to the rest of the forming and fabricating community to broaden our scope. And then we will discuss press room topics in May, and then education and development. And that's a 6-month rotation. And what I want to do is just every 6 months, we can just cycle through that rotation again, so that anytime a topic comes up and someone says, hey, I really want to learn more about a topic that has to do with materials, I don't have to try, and Brianna and I don't have to try to figure out where that fits in the schedule. We already know that there's an opportunity to talk about materials in March, and we're going to also take another opportunity to talk about materials in September. So this is kind of the editorial calendar that I'm proposing for our technical talks that we have each month. And already within that, we know that in April, we're going to be joined by a gentleman named Chuck Summerhill, who works for Rollcraft, and they're a roll forming outfit. And Brianne's been working with Chuck to bring a kind of a roll forming basics or roll forming fundamentals technical talk to our stamping and dies tech group and to the forming and fabricating community. So hopefully this will help spur your guys' input and Brianne and mine's own creativity on coming up with topics and guest speakers to have present each month. So next month we will talk about materials, will be the general theme. I'm not sure whether or not we're going to be talking about tool materials or the stamping substrate materials or coating materials. Um, does anybody have any particular uh, preference today? If we were going to talk about materials next month, is there something about materials that you specifically would like to learn more about? Okay. Right. So like last time we talked about materials, you led the discussion. We were talking about different types of tooling materials and their characteristics as far as workability, weldability, repairability, etc. Right? And so, is there another broader theme that we would like to drill down a little bit deeper, right? I know some guys that, if I talk to Stu Keeler knows a heck of a lot about material plasticity and material plasticity theory, uh, being the godfather of sheet metal forming and formability. My good friend Danny Schaeffler, he's kind of a metal, a steel substrate specialist, bringing in a lot of steel experience. And we used to have a very active member in in our tech group who worked at Bowler Udelholm, and they always talked about these new advanced materials for the tools themselves. So I mean, anything that does anybody have anything in particular they'd like to learn more about regarding materials? That big umbrella of sheet metal, the sheet we stamp itself, or the tool substrates or coatings. Uh, just to narrow down who I should try to rope in to be our guest speaker next month. Ooh, see, there we go. Right. So when we talk about clad materials, we're talking like what, like aluminized materials, right? Just where aluminized, galvanized. We could talk about tin plated, things like that. So all how those materials behave, and that's a great one. Yeah, I think I'm. That's an interesting topic. Yeah, see, there we go. Right. I have zero experience with that. So, but yeah, that's cool stuff, right? I think I know people that we can talk to about getting at least some discussion going, talking about this idea of pre-painted or pre-coated or clad materials and their behavior and things to expect and things not to expect. I can think of a couple people I might tap to be guest speakers. So that's actually that. See, that worked out pretty well, right? Give ourselves a narrow theme to talk about, and then just drill it down in one aspect. So thank you very much. I look forward to that. Elastomers. So we could say, yep, non-metal. Okay, cool. All right. Well, we'll see. We'll see which direction we take, and hopefully, by the time we send the agenda and the meeting reminder out, we'll have narrowed it down to some flavor of discussing those materials that we stamp, whether they're not metals or non-metals, whether they're clad metals. Sandwich materials are always interesting. Patch blanks are very popular these days, elastomers. So there's a lot to discuss. So more things to discuss in the future, and hopefully I have the next 3 weeks to figure out who we can get to talk about any one of those topics. So thank you. All right, and don't forget also in April, that topic's already pretty much narrowed down. We will be talking about roll forming, so we'll be going away from traditional stamping and die-based stamping and going into coil processing techniques and roll forming. And our guest on that meeting will be Chuck Summerhill from Rollcraft. All right. And hopefully a few hundred people attending our meeting. Okay. Yes. Does it? See, I picked the topic pretty cleverly. Actually, that was a complete accident. But that's during the Big M, huh? Oh, Natalie. Um, we could we could broadcast the meeting from the Big M. We could have a live meeting and a web broadcast at the Big M, but we need a meeting room at the Big M. But that would be super cool. Yep. Groovy. Okay. Yeah, that will be super cool. I'm putting that on my calendar right now that I plan on doing that. So that would be super cool. So let's see. Groovy. All right. Yes. Okay. I'm sorry, Sam. Well, you made it for all the administrivia, and I was just about to start the technical talk. I'm sorry, buddy. Okay. All right, thank you very much. Okay, so today's technical topic was design for stamping, right? And this was a topic that was triggered through some questions from Brianne and a couple other folks who have said that they're new to stamping and they wanted to know a bit more information about um, criteria or guidelines on how to recognize whether or not your part is a candidate to be stamped. If it was a part that was perhaps being formed in a different method or a different format. And so I went through and I gathered some criteria that I used to use in a course that I taught at SME probably about 12, maybe 14 years ago, we used to have a class at SME, which was called Design for Stamping Manufacturability. And myself and Jerry Poole from, he was at that time was a retired GM employee. We put together this course about criteria on recognizing if your design was in fact suitable for sheet metal stamping and design for manufacturability. And one of the things that spurred us into putting that course together was that a lot of times people talk about design for manufacturability, and they're actually usually talking about design for assembly, right? Or sometimes you talk to people about design for manufacturability, and they're in fact talking about machining, right? Or other manufacturing methodologies. And that we found that the design for manufacturability standards that were in those very generic books were not necessarily suitable for sheet metal stamping. So we put together our own guidelines, or Jerry worked together with his experience and took from his experience at GM and put together these guidelines. Um, One of the things that happened that when we were going through this and we're trying to write these guidelines on what can and can't be stamped, we ran into the fact that, well, given enough time and money, most anything can be stamped. And that's pretty true. I mean, most every die maker that I've run into they'll say, well, you can't make that in a die. And then a few minutes later, they'll say, well, maybe we could if we just did. And they'll list off a long list of things that may or may not be very realistic to achieve in a production environment. So, first of all, before I start going through any of these guidelines that I've documented, I just want to remind everyone that design for stamping manufacturability is really this idea where we were trying to establish some base point guidance so that designers of stamped parts could recognize whether or not their product designs were suitable for, I'm going to use the dangerous word of optimum stamping production. And that when we discussed these standards, the standards that I'm going to show throughout today's presentation, were how one particular automotive OEM, their sheet metal stamping die design group, defined those criterias. And that these criteria, I know, are not going to make sense for all markets based on the different production rates or production targets or quality targets, and they're not necessarily going to be universally applicable due to the size of component or type of component, right? But I just wanted to first of all just put out what kinds of standards people throw out there, guidelines people use to talk about sheet metal stamping, and then maybe once we establish a baseline, we can talk about how those rules or guidelines would change if we knew in fact we were designing a different commodity type for a different manufacturing vertical. So general definitions, just to be clear, when we talk about die, whenever I talk about dies, I will be talking about the tool that is used for the serial production of sheet metal stamped parts. Right? So whenever I use the word die inside this presentation, it's going to be talking about sheet metal stamping dies. If I use the word process or processing, we're talking about the sequence of operations that is used in a die or a series of dies to transform the sheet metal into a value-added product. So for example, in this illustration on the right-hand side of the screen, I have shown a process, and this process is going to take the coil stock, chop it into blanks, through the use of a stamping die, take that flat blank, give it some shape, use a cutting operation to trim it, use a cutting operation to pierce some holes in it, and use a flanging operation to bend over the edges of the material. And this defines a process. And I would actually call this a 1, 2, 3, 4 die process, where we know that there's 4 unique tools that are specifically being used to process that flat blank into, in this case, that picture is like of a car or truck door. Uh, yes. Exactly, right? So when we talk about progressive dies, when we say we are blanking in a progressive die, we are not cutting the piece of material 100% free from the coil, but instead we are freeing up a section of that part and leaving it attached to the coil. So imagine if we were in the business of stamping uh, miniature car doors, right? So if this was not a full-size vehicle door, but a miniature door, we could, right? Well, those are die cast. That's a different thing, but right. Imagine if this thing was still attached to the coil, right? I could imagine some coil stock being left attached to this little rectangular blank, and then when a first operation inside of a progressive die closes, it puts some shape into that rectangular piece or square piece of material I'm carrying with the coil, right? I could then pitch that material a little bit forward in the process, do some other trimming or cutting operations, pitch that a little bit forward, poke some holes in it, pitch it a little bit forward, bend some edges over, and most likely I would have a final operation where I would separate this completed part from the coil. So exactly that, that's you're totally right when you ask that question, Doug, right? The a progressive die is just a single die that has a sequence of these operations: blanking, forming, trimming, piercing, flanging, built into one grand unified tool, that each progression of material through that tool is doing a little bit more work progressively to that coiled sheet metal, and the very last station separates that finished workpiece from the part. Sound good? All right. And finally, basic definition. If I talk about press or press direction or press ram, we are talking specifically about the machine that is used to operate those tools that we are using for sheet metal stamping. So the press is the device that operates the dies. So one of the things that I went through when I first started working in the metal forming industry is I worked with lots of really clever people from very diverse backgrounds. I worked with folks who were tool and die makers with 30 years of experience in a single site. I worked with these guys who were big brain PhD types who were working from an academic background and trying to apply it to sheet metal forming. I worked with one of the world's foremost experts on die casting who was dabbling in sheet metal stamping because he found it was an interesting problem that had interesting variations that he wanted to tackle. And when we started talking about what determined whether or not a die or the die process that that die was used to be used in was good, is we decided that anytime we think about a die, that a die it must do these four basic things in order for it to do its job. Right, so anytime we think about a die that we're going to use for stamping sheet metal, it should have some way of locating the workpiece, the piece of sheet metal inside it. Right, so if you take a look at this little cartoon that I have on the side of on the slide, and you can see that I've just taken this blank of metal and I've shown it resting on top of the forming die. Well, this die can't do its job very well unless I create some very basic or very complex mechanism to make sure that the workpiece is properly located inside of that forming die or that draw die. And whether or not this die works very well will be driven by how well I can locate that workpiece. Every good die has to be able to hold the workpiece. That means that if I want to do some cutting in the second operation of this cartoon, you can see that I have areas adjacent to the places where I want to do some cutting and trim off this excess or scrap material. I need to have sufficient area to grab onto or hold onto the workpiece, and that many of the things that might go wrong inside of a stamping die regarding quality or repeatability of a process could actually be the fault of not having sufficient area in the design of the part or of the process to hold on to the workpiece as we're trying to do the work. Of course, the die's got to be able to do the work, right? It has to be able to work the sheet metal. And when I talk about work, I'm talking about cutting, compressing, stretching, uh, shearing the metal, stretching the metal, right? Putting energy from the press ram through the die into the material. And finally, when we talk about whether or not a design is suitable for stamping, there has to be a way to make sure that this part can leave the die, right? If you have a part that's being formed onto a die, but once you finish forming it, the part's clinging to the lower die or to the tool, well, that's not helping you release the workpiece, right? And one of the jokes we would have when we were doing these design reviews, and people were designing impossible geometries in sheet metal, if they couldn't be released from the die, we would joke around and we'd say, well, we can just ship a die with every part that we sell. So if you're not releasing, working, holding, or locating, it's usually one of these things going wrong when people come back to you and say, that can't be done in a die. Now, furthermore, any of these dies that we design to form these sheet metal parts, of course, we want to support a minimum amount of variation in production, right? So, if there are design decisions that are being made that we know would lead to poor repeatability in production, oftentimes a die engineer or die processor would tell you that can't be done in a die. We also tend to write these guidelines to minimize the initial tool cost for tool build and construction. And hopefully we're also writing these rules to support a minimized cost and time to repair and maintain. Now these two things right here, the minimized initial tool cost and minimized tool repair and maintenance, these things are actually quite often at reverse purposes to each other. A lot of the tool and die standards that I've seen from different companies throughout the years, I've seen standards that you could tell were written by someone in the design and initial purchase group because they favored cheap initial tool build and tool construction, but hurt you as far as maintenance and repair. And then you'd see other die standards that were written to favor repair and maintenance that resulted in challenges for keeping the initial tool cost down. So that's one of the challenges we have when trying to design a good stamping process is trying to find that right balance between, well, I want to build it cheap, but I should be able to fix it or keep it running relatively cheap as well. So the work that dies do, we discussed this very briefly before, and this was one of the topics that Brianne went through in the January meeting. I'm generically going to say pretty much dies do two kinds of work. They're either forming the sheet metal by stretching it, compressing it, bending it, flanging it, or folding it, or the dies are cutting the material, which could include trimming, piercing, or blanking. So one of the things that we look for when we're looking at a product and trying to determine whether or not that product is a good candidate for stamping, one of the things that we look for is whether or not that tool, that part, is one that could be formed inside of a die that's going to facilitate the use of simple in-die work, right? So the most simple way to do work inside of a die is to attach your tool to the press ram, attach your upper tool to the press ram, attach your lower tool to the bed or the bolster of the press, and bring the ram down along a simple linear vertical axis and do the work to that piece of sheet metal. Now, of course, when you start looking at parts that have a bit more shape to them, like the part that I have illustrated on the bottom of the slide here, you can see that there's this area that I've color-coded red in that illustration. What's actually happening in that part is that the areas that are in green are areas that are easily accessible along that vertical action of the press. Right? So those are areas that are easy to form in a conventional stamping operation. The area that is curled underneath, this area that I've circled right now, cutting a section through there, this geometry is bent underneath and would not be accessible to the press ram. Right? Now this is what a lot of people would call a backdraft or die lock condition. And when we talk about things that are easily done in serial stamping and high volume stamping production, things that have a significant amount of backdraft are difficult or challenging to form in a repeatable operation. Right, so earlier Doug asked about progressive dies. When people talk about progressive dies, this is one of the things that they look out for as to determine whether or not this is easily done in a progressive die. If I have this geometry that's bent back on itself, if you imagine what the tool that would have to form that would look like, right, I'm just sketching in a quick section of what could be a proposed tooling geometry. But after that metal gets formed to that geometry, to this little kind of horse-headed shaped horn, then the part would kind of be clinging or stuck to that lower geometry. Now you might say, oh Eric, that's easy enough. I could just pick the part up along this axis. But that's something that's not always easily done in a production environment. So this would kind of raise the bar. Yeah. Right, exactly. So like what Doug's pointing out is that if I had to form this kind of curved shape inside of a progressive die, maybe the geometry coming into this particular station would already include a certain amount of this curvature, so that if I hit it with a tool traveling in my vertical press direction, it would bend the rest of this already preformed curve the rest of the way around that horn, right? But there would still have to be something here supporting that area adjacent to the bend. And depending on the size of this curve, the amount of geometry, the amount of tool that I have trying to support that area could in fact create a trapped workpiece. Right? So this is one of those things where someone would say, oh, we had this part that had maybe just a small roll of a few millimeters, and we were forming that last year, no problem. But if you had a shape that had much more of this backdraft or a larger backdraft condition, somebody would say, well, this design with a greater amount of backdraft, we can't make that in our tool, but there is a different design with a shorter flange, and maybe that could be. And this is one of those reasons why those guys from manufacturing might look at a product design and just kind of shrug their shoulders and say, well, we can't make that. Well, sure, it can be made, but it's maybe something that they're not willing to do in their manufacturing environment because of limitations of their robots or limitations of the progressive die's ability to pick the part straight up and pitch it over. Right? So those are all things that, sure, can it be done? Quite often. Is it something that we can do in serial production based on our standards or tooling standards? And that's where you usually run into a little bit of trouble. And this is also one of those things that causes a lot of trouble when people consider prototype versus production. Right? The number of times I've heard people standing there with a prototype part in their hand telling the tool and die guys, don't tell me it can't be done, because I'm holding the prototype in my hand, right? I have a piece of metal in my hand that somebody made to look exactly like the thing that you're telling me can't be made, right? And a lot of times prototype parts are parts that are being able to be done in a process which is maybe not conducive to that serial production. Right, so sure, I can make 5 of these at a time in a prototype shop. You want to make 5,000 of those in an hour? I don't know if I can pull that off because I'm going to use a different methodology. Right? Some of the things that can happen regarding, when we look at this product design, um, it is possible if we have this geometry I've kind of sketched in this kind of green section here. You can see that this part has a little bit of backdraft in that section. One way that a person can get around this backdraft condition is by using a cam. So rather than relying only on the vertical press action, they could in fact use a cam, which is just a series of inclined planes that take the vertical action of the press ram and reorient that work along a different axis. And that would allow you to form this backdrafted geometry. This backdrafted geometry would still need to be somehow removed from that die, but it still is a way of getting that shape. So the shape is in fact possible, right? There's nothing really prohibiting that shape from being generated, but it's something that maybe is a little bit more expensive to do, or perhaps takes a little more time, right? And when things take a little more money and a little more time, those are the types of things that make manufacturing engineers say, we can't do that. Another alternative that is always available is if I reoriented the part inside of the tool that was going to be used to make that. Instead, I took this exact same section and I just rotated it a few degrees over. Now I have the ability for the press ram to fully have access to that geometry to form it without having to worry about introducing a cam. And now people would have to be curious if this little embossment section here was still capable of being formed in that same operation, or would they have to use a sequence of operations to spread that work out in a progressive or transfer type format? So it can be done. It's not impossible, but it is something that makes stamping a bit more difficult. So these are a couple pictures that came directly out of the old SME course for Design for Manufacturability of Sheet Metal Parts. This was one of the things we used to recommend to people. If you have your part and you orient your part in a typical, what we would consider the draw or in-die stamping orientation, one of the things we were trying to achieve is that these wall angles of the part would be 6 degrees from vertical or more, right? So if this is vertical that I'm sketching right here, we want to see that this included angle was 6 degrees or greater, right? And that would assure that our parts were being able to be formed using the direct action of the press without having to employ retipping or employ the cams. And that would keep the manufacturing environment optimal for what that automotive OEM considered normal business. When we saw that these wall angles were tighter than 6 degrees, then what we saw is that increased the die cost, that made the dies a little bit more difficult to build and maintain. It also had this other effect that it turned out 6 degrees was also the optimal shape to have if we were racking these parts and stacking them on top of one another. A 6-degree open wall angle allows for these parts to stack on top of one another relatively well without causing them to yaw open or spread open if you are racking these parts, right? When the wall angles were 6 degrees or under, not only did it add the die cost, but it also added assembly costs because racking the parts and storing the parts became more difficult because we couldn't just stack them on top of one another without having to worry that the ones on the bottom of the pile were being squeezed shut in a way and the ones on the top of the pile were being spread open. And we also recommended that if you saw that included angle was less than 0, right, that suddenly creates that backdraft condition, then we saw that introduced the possibility of needing a cam, right, and adding cams increased this kind of die cost. So these were the things that we were looking at. We had a roughly, I'm not going to be able to go through all of them today. We probably had about 15 different criteria pictures similar to the one that I'm showing here that gave recommendations on things that were achievable in draw. Right? We had length of line change, because we imagine if this part was being formed from a flat blank, this section length through this geometry A was more or less being stamped or formed from whichever flat length of material spanned between those 2 points. Right? If we saw that difference in length of line, right, measured through that section A, if that difference between the straight line length and the section length through the part itself was greater than 15 degrees, well, that meant quite often that that material would be stretched quite a bit on average, and it might increase the die cost because we might have to create a progressive operation to partially form that geometry, then reform it again later. Right? If we saw that go over 25%, we found that there was quite often severe limitations in their particular stamping environment in the ability to be able to form that part. So this is just one example of ways that people try to determine the stamping manufacturability of a part. So on, let's see, this slide right here, I believe you should be seeing a little animated GIF or animated GIF, if I pronounce it the way the internet tells me to. That illustration you see there is a rotary cam flange. And remember what I said about what every die has to be able to do. This animation is a good example of it. We see the workpiece being loaded. We see that the tool has sufficient geometry to match the part shape so that it could orient or locate that workpiece inside of the die. We also see that there's sufficient area for this upper tool to be able to hold onto the workpiece adjacent to the work being done. You can see that this cam is transferring vertical action from the press ram into a horizontal action and doing the work. And then finally, this rotation of this lower filler enables us to easily strip that part or remove that part from the tool. So this is an example of the lengths that the designers would have to go to achieve those 4 basic criteria that I mentioned earlier. Every die has to be able to locate, hold, work, and then release the part. I think I heard someone want to comment on that. Okay. Yeah, that's actually an animated GIF off of a video that I have on my YouTube channel. Right? That makes a clearly more expensive die. Now, this is one of the things that happens is that imagine this is a automotive component like, I don't know, this would be used quite commonly in your fender. Right? And this is, if you can imagine, the show surface of your fender is on the top of this die, and that area being bent underneath, that's the area that you're closing your hood into. That's the shut face of your hood. And right, this tool adds a lot of complexity, but that's geometry that's 100% necessary for the function of a fender. Right? You don't have fenders if you don't have that surface going vertically down into the hood's shut surface. So this is one of those things that, yeah, there are criteria that we had. We told people not to design these backdrafts, but it just made for a way to do it. Given enough time and money, pretty much anything can be stamped. Right? The picture on the left is just an alternative way of getting that same type of geometry in. However, you'll notice that without the rotor, this area that we're using to locate that backdraft, and also the area that has to be able to transit out from underneath the flange in order for the part to be unloaded, now you'll notice a much larger footprint of the die in order to do what was being done in that small rotor area. So this is an innovation that came up recently, and this is one of the ways that we're able to make more complex shapes in fewer operations in automotive stamping operations today. Other guidelines that are common when people talk about whether or not things can be stamped is cutting and cutting angles. Right? Again, I got that illustration of that part that I showed earlier. You'll notice that I've highlighted all of these boundaries around these little holes, as well as the boundary around the part perimeter, and it's shaded green, yellow, and red. And this is an output from an engineering software that I use every day, which is measuring the slope of the area perpendicular to that part boundary. And what it's measuring is the trimability or the cutability of that material. Now, whenever we think about cutting or trimming or shearing or blanking material in a stamping die, one of the guidelines is that you want to be able to imagine that if this is your sheet of material, you'd really like the shearing element, the cutting element, to be able to cut that material at almost a right angle to the material plane itself. So if my sheet is horizontal, I want my tools to come in working on a vertical axis, and that's going to give me the best shear or the best cut of the material. Now, guidelines that you'll hear people bounce around when they talk about thin metal stamping, right? Material under 1 millimeter or so. They'll have guidelines in their head like, 15 degrees from horizontal is still trimmable, right? And they'll say if I have anything steeper than 15 degrees from that horizontal, if you imagine the section being steeper than 15 degrees, imagine what the die would look like in order to cut that material. If that section was steeper than 15 degrees, the lower cutting steel would be sloping severely downward, and that would make it very difficult for us to keep the material from rolling off of that support surface during the cutting operation. So quite often when you have these wall angles that are steeper than 15 degrees in your area that you're cutting, what you'll end up having is you'll end up having a poorly sheared material. You'll have a lot of increased amount of burrs. You'll have a lot of additional wear in your tooling steels because your steels are not shearing the material quite as easily. If we consider the inverse of that sketch, and I'm trying to trim on a part that has this 15 degrees going uphill towards the trim line, now what you can see is that my lower steel creates kind of this knife edge condition. And with this knife edge condition, I'm also going to have increased incidence of burring because the part can chip and lose its ability to, or the steel can chip and not stay sharp as easily. You can also have severe die collisions because as the upper steel tries to come and cut along that steep slope, it can actually skid inward a little bit, and that would cause the upper steel to clash into the lower steel and actually beat up the tool a bit more. So that's another reason why you'll hear people when they talk about is it stampable or is it not, they'll be talking about trim angles and trim locations. When we talk about a traditional or conventional tandem line of stamping where perhaps we're using robots or pick and place automation in order to do that, for the part that I've illustrated here, well, if we just rotated this part a few degrees counterclockwise, all of these steep areas that are being shown in red as being untrimmable would now be closer to horizontal, and we'd be able to trim them just fine using the vertical motion of the press. However, if we're talking about high-speed transfer presses, or if we're talking about progressive presses, the ability to try to reorient the part from one operation to another might in fact limit our ability to try to reorient the part to achieve trimming. So again, this is one of those things where the die processors I'd work with, they'd say, we can't pierce that hole or we can't trim that hole. It's that It's not impossible. It can be done, right? We could introduce cams that travel along an alternative axis, and that could possibly do the piercing or the trimming. But it's something that we perhaps were not willing to do. So similarly, I have a few tables that were published with SME when we put together this Design for Stamping Manufacturability course, where we would say, here are some recommendations for various holes of various hole tolerances, and what would be the acceptable trimming angle relative to that. So this was for holes with a given plus minus tolerance, given a certain hole size. Here were some limits of piercing angles that were possible in order to assure that we had the right size and shape hole. The alternative, if you can't achieve your trimming or piercing using the direct action of the press, then you can always employ these cams. And again, you can see my cam coming in here to do that trimming operation. All right. Now, trimming operations like this using cams, this brings up many of those other issues we talked about with what it takes to be a good stamping, where parts that we need to have cam trimmed, one of the challenges we have is getting this trimmed piece of scrap out of the die. Right? So when I said there were 4 things every die had to do, they have to locate, hold, work, and release the workpiece. They also have to be able to release the scrap. And if you have a complex die with these cams moving around, it's sometimes a real challenge to make sure that this piece of scrap makes its way safely out of the die without getting trapped or ruining your tooling. We had guidelines for piercing. Believe it or not, there were guidelines on how close together we recommended having your holes. Right? You don't want your holes too close together, because if you imagine the tools that are going to be used to do the piercing, here's a picture of a pierce punch retainer. And if every hole that we're piercing is using one of these retainers in order to hold the pierce punches, there's a critical mass of number of holes and closeness of holes that you can achieve before you have to go to a custom made or custom fabricated retainer. And because the company that I was working with at the time that was documenting these manufacturing standards was targeting high volume serial production of automobiles, they tended to err on the side of, we need to be able to use off the shelf, out of the standard catalog components. And every time we saw that we had to custom fabricate something, that was seen as a huge increase in potential cost, not only for the initial tool build itself, but if heaven forbid we break one of these retainers and have to replace it, if this is a custom made thing, we would have to have 2 of them on hand at all times, or we would have to risk shutting down production for a long time as we waited to custom fabricate another one of these retainers. So that was another reason why we had to make guidelines for our product engineers, telling them, don't have your holes closer together than, I believe it was 2 times the diameter of the hole sizes themselves was one of the standards, right? Hole to hole standard, we don't want them too close to one another. We don't want the holes too close to a trim line, because then we wouldn't be able to use standard off-the-shelf piercing buttons. If the trim line's too close to that pierced hole, next thing you know, we have to make custom-made inserts for our stamping operations. So these became things that we would use to help educate our product engineers on how we were designing our parts to best suit our manufacturing environment. And these rules, a lot of stampers that I know and a lot of smaller shops, I'm sure Brian and Brianne are looking at this going, well, gee guys, I mean, you're being very inflexible. Well, that's why smaller shops like yours exist, is that you guys have flexibility and fewer rules, I suppose, of what's possible in your shop than what a a giant, massive OEM stamping environment would possibly have to live within. Right? So we had guidelines on piercings or different ways to design piercings. So here was an example where somebody needed a hole through the part, but the hole was on this angled surface, and otherwise we would have to have a cam to come in and pierce that hole. Well, it turns out if this hole was not critical in its function, we could actually create this little localized depression, this little frog eye depression, and we put the hole on that. And it turned out that making that recommendation in this case not only made piercing the hole easier, but it made the part actually function better. The product engineer was able to design exactly the embossment they needed to get the hole exactly where they needed it and a nice tight roundness tolerance for that hole itself. So that was kind of a win-win. We had guidelines on if you have holes on complex surfaces, things that are possibly going to increase the complexity of your stamping or not. So is there any way that we could come up with kind of a universal guideline for stamping manufacturability? Probably not. Right? Because I already know that right now Brian is probably thinking about, he built these dies that were cutting slots in tubes. And these slots, if I remember right, were the beater brushes for a vacuum cleaner. And not only were they slots, but they were slots that actually went around the curvature of the cylinder. Right? And this probably would have violated absolutely every one of the die standards of the tool and die shops that we put together these guidelines for. We would all say it's impossible, you can't do it. Get yourself a get yourself a laser and cut that stuff, right? And right? Yep. It's a very special die, a very special knife, and right, when we think about the things that I discussed before, right? A big challenge for you was most likely getting this cylinder after it's pierced off of the tool or the fixture you used to pierce it and making sure that the scrap was safely released, right? So, anytime I think about can I stamp that, I really try not to think so narrowly like these standards, but I always think about those four things that I said. We have to be able to locate the workpiece in the die. We have to be able to hold it. We have to be able to do the work. And we have to be able to release it. And if we can work our way through using our ingenuity and our creativity on how our dies achieve these four things and achieve them well, then we have a sheet metal stampable part. Right? And if you can't do this thought exercise with your product geometry and with your tooling geometry and come up with reasonable solutions for all these things, that's when I say, yeah, probably the part can't be stamped. All right.
Eric, I have a question about those angled holes that you had besides that. You're assuming that's all done with a single die, right? So that, otherwise it'd be fairly easy to cut it and stamp it in the hole from the tip side.
Correct. Right? That is a way to do it. So I mean, I want to say that when we were talking about this particular hole here, there was a assumption of a tolerance for that hole, right? So if we were to make the hole in let's say when it was on a flat blank, and then do the embossment after the hole was formed, then our ability to maintain the hole's roundness would be called into question, right? Um, this applicability where we see the holes on, like this one right here, where the hole lives on three different planes. The reason why they didn't like this standard, and I it was General Motors, right? It was the Fisher Body die standards we were working from. We didn't like piercing on this, piercing these holes, because in order to do this hole the best way possible, it meant at the very least two separate piercing operations to cut out this complex uh, hole that lives on three different planes. And because we'd have to do that in two operations, those would be two subsequent operations, each of which has a little bit of tolerance stack up in between the two, and we wouldn't necessarily be able to deliver exactly the hole people were asking for. Right, so our criteria when we were putting together these standards was how easily can we in our manufacturing environment deliver to you what you're asking for as far as product geometry. And if somebody said, oh, this hole has a wide open tolerance on it, then we'd say, oh, no problem. We'll pierce that out in one operation, or we'll pierce it out in two subsequent operations. No big deal. We'll pierce it out in the flat blank and form it after. That's all in play, and that's why it's really nearly impossible to write a single standard.
So, but what does a wide open tolerance mean for being able to do that? Say that last. That's very vague.
Yeah. Um, when we were talking and again, this is automotive metal stamping, and we were talking about thicknesses of material around zero point 0.7, zero point 0.8 millimeters in thickness, right? Is that if we had to separate a piercing operation into two subsequent adjacent stations, then we couldn't vouch for less than a tolerance tighter than 1 part thickness. Right, so you want a perfectly round hole, but that round hole lives, right, I'm trying to sketch this kind of section view. Here's a top view of this hole right there, right? And imagine that this is the break line of that bottom break, and here's the break line of that top break. And someone says, I want a perfectly round hole here. Well, it has to be a hole in this plan view, but I'm piercing out this top section in one hit and the bottom section in the other hit, there's very likely going to be potential for a seam or a gap in those two areas that I pierce. And it was not common that we could promise people something better than 1 part thickness of trueness of this match between these two adjacent cuts. Right? And a lot of that had to do with the fact that if you're doing your piercing in subsequent operations, that you're not going to have a perfectly flush location and a perfectly flush positioning of the part on the tool that you're using to cut it when you're indexing the material in, whether it's a progressive die or a transfer die, that you're going to have a little bit of wiggle between one operation and the next. If I want a perfectly round hole, I have to pierce it at once, right? Does that make sense?
Right. I'm not sure why you have to have two separate piercing things. They can't just do it all at once.
But if there's two different surfaces that you're piercing instead of three,
In this,
you're
yeah,
piercing on two lanes instead of three.
when we're
Two operations.
when we're piercing on these, with these three planes, one of the issues was that if you have a pierce punch that's trying to pierce through this all at once, right? You had this tendency that you're trimming. Again, this is a section view. I'm not really picturing it in 3D very well. But what will happen is that there will be a good length of this cut that we're making, which is going to be steeper than that desired trim angle of close to horizontal. And I'll be cutting on a very sheared wall. And anytime you're cutting through a sheared wall, you're cutting through something that's a little bit thicker than metal thickness, right? So if I have a vertical action of my press trying to cut along an angle, even though my part's only like 1 millimeter thick, when I'm cutting through a steep angle, I'm cutting through greater than 1 millimeter. And what ends up happening is that you end up with a fair amount of thrust on this pierce punch as you're cutting on that kind of an angled surface. And your ability to hold the tool on that type of a cutting operation was a problem. So our die engineers would normally, in this kind of situation where they're making these complex multiplanar cuts, they would try to pierce, right, let's say the top section out first, then pierce the bottom section out second. That would give them the ability to have a nice, robust piercing operation that didn't beat up on the tools so much. They might even use cams to come in and cam pierce this top section out first and then direct pierce out the second section. And then you'd have two adjacent operations trying to cut the same feature out.
I see.
Right? And again, this is just. Go ahead.
I was going to say, I was going to change subject slightly. You mentioned that ground operation versus a lower volume operation would have perhaps a different approach. So if you're looking at the drawing in the lower left corner, you might have depression.
Yep.
Yeah, is that something that you would need to do as well if you had a lower volume type operation, or would you be able to still do the original form?
The lower left, that'd still be kind of challenging. That might be an angled tool if you're cutting it at on a plane like that. It might be regrinding a tool.
Right.
Is that
Just
use cam?
yeah, most of them can.
Right. So there's plenty of possibilities, and we're cheating because we're looking at these little localized sections, right? Because we don't know what's going on in the rest of the part. Because one of the things that you could do is reorient the part, right? If I could just take this part and rotate this part, 30 degrees clockwise, I rotate this 30 degrees clockwise, and this hole is now on a horizontal plane, and I can pierce it no problem. But it depends on what's going on with the rest of the geometry that's not on the screen here. And when we were working at GM, reorienting the part in flow was something that we tried to avoid to do because we wanted to form some of our parts at 30 strokes a minute. And at 30 strokes a minute, we said we don't want the automation trying to make these parts pitch. Right? We didn't want to rotate them, so we just wanted to make them in one orientation every single hit because we're making thousands of these things in a production run. Um, when we talk about smaller job lots, especially the aerospace guys, aerospace guys' career job lots are what we were making in a couple hours in automotive stamping. And for them, they're like, yeah, rotate the part, no problem. They're like, you guys are being silly. Why don't you just rotate the part? So again, it's really hard to come up with some sort of single guideline that would apply to everybody, and that's why we ended up simmering it down to those, the only real rules. Worry about doing that, right? And if it costs you more money than you're willing to spend to accomplish one of these things, then you know that you have a design that's a candidate for redesign.
And it shows the difference in what can you say, what companies are willing to do, because of how fast you have to get the part done, how many reviews you need, and, how easy we can get a different job sometimes.
Yep. One of my customers right now, if they were faced with this particular design on the lower left right now, they would tell me no problem because they're going to have an in-die hydraulic piercing operation that when this rest of the geometry was being formed, as soon as that bottomed out and reached bottom, they would come in with this in-die hydraulics, pierce that out, no problem, retract the pierce punch out, and pick the part up and move it on its way. And they're like, there, see, no problem. One hit, we put the shape in, and we put the hole in. And I'm like, well, okay, that works for you guys, but not a lot of my other customers would be willing to do that. They're not going to put in die hydraulic that lowers the stroke rate from, instead of doing a stroke rate of 20 of these parts in a minute, now they're making 3 in a minute because they got these in die hydraulics doing piercing operations in the same hit as forming. And they said, well, that's our business model, that's how we live, so that's how we do it. Cool. Cool discussion.
I've got one other little angle on die design. Um, the place that I worked for, we had limited size of our presses, so we could only use limited size die sets. And this one in particular I could think of, they jammed, in my opinion, too many stations into one die, and it was using cams
Yep. Right. So, given enough time and money, we can make anything work, right? Whether or not that ends up being worth it is always a challenge, right? Other things that I've seen where design decisions were made um, in order to achieve certain shapes. This rotary cam, I went back to the rotary cam picture that we showed earlier. Um, One of the general rules is these rotary cams, you can only use them on relatively straight brake lines, right? You would never want to use this on a curved brake line, let's say in the area on the nose of an automobile hood where there's a lot of plan view curvature. And one time I've seen them apply these rotary cams to a hood that had a rather pronounced round bullet shape to the nose, and they were using rotary cams from about 10 o'clock to 2 o'clock on the arch of this nose. And what ends up happening with these rotary cams, I mean, they have to rotate cylindrically. They ended up with, I believe, 15 of these rotors spaced across that curvature of the nose. And they had to be timed to rotate in a certain sequence and rotate out in a certain sequence because they would kind of key into one another into that finished curvature. And that took the production rate of this particular product from a targeted around 10 strokes a minute down to about 5 strokes a minute of production volume. So that cut their production volume in half. And so it cost a heck of a lot more money to form that one product than it was really intended to. So, yeah, it can be done, but not easily. Cool.
My other comment is I love CAM technology, and it feels like a lot of this stuff has been taken away by electronics. I'm glad to still see that my love of CAM technology is not going to put me at a disadvantage.
Oh, cams as opposed to servos for everything or electronics?
Yeah, yeah, I love antique engine shows and everything, the different operations that you're using CAMs.
You know, simple mechanical cams and the application of that basic mechanical principle is, I mean, it's just super sound. I know that we had a bunch of these in-die transfer units at one of my customers. Well, shoot, quite a while back, more than 15 years ago. But we were looking at these in-die transfer units, and they were all cam driven as opposed to servo driven, and they never ever had a bad automation or transfer crash because the it was pure physical closing of the die pushed those in-die transfer units into position, and when it opened, it pulled them out. And they went away from that physical cam behavior to a servo behavior, and then all it took was a minor programming error, and you had the servo motors slamming the expensive pick and place fingers of this transfer, slamming those into your expensive dies, and you don't have those problems with a well-designed cam. Cool. All right, so I guess the to wrap things up because I kept you guys well over the normal time span. Right, what can we do next within SME? Right, one of the things that I will be doing is I will be I certainly invite people to take the guidelines that I have. I'm going to take the guidelines, I'm going to put them most likely on my blog area and open them up for comment, questions, etc. And possibly use that as the basis to try to drive broader definitions or maybe narrower definitions of those guidelines to support other commodity types. I also invite anybody who's participating in today's meeting, if you guys have seen similar guidelines, similar standards, catalogs, old die design guideline books, other people's blogs, other people's books that make recommendations on how to do things like this, share those with us within the community, and we, the members of the Stamping and Die Tech Group, will help curate and share that knowledge with the rest of the community at large. And hopefully this gives us opportunity to educate our community more on the reasons for standards and guidelines, because I feel that if I didn't discuss the reasons and the background behind those illustrated guidelines that I put up today, I might, really upset people because that was one company's methodology to arrive at its goals. And for your own company, for your own goals, um, if it's better we understand the logic behind how those were defined and why those guidelines were picked, as opposed to just knowing what the numerical guideline was. What other questions, comments, or snide remarks from the Peanut Gallery today?
No, thank you. It's very interesting. I mean, new information.
Thank you very much, Doug. I'm always glad to hear from you, and I'm very much looking forward to hearing more about this design show you're going to.
All right, yeah, send me a list of signatures if you like. That'd be helpful.
Oh, if it has to do with stamping, metal fabrication, metal bending, and it's interesting to you, it's interesting to me.
Doesn't
All
have to
right,
be
sounds good.
doesn't have to be
What
metal.
was that?
Doesn't have to be metal.
Okay.
I'm monotheistic that way. It's all metal.
Well, we'll have to show you some pictures of some of the non-metal stuff we've done.
Oh yeah,
Northeast Ohio is a big polymer center as well.
yeah,
So yeah, we do have some interesting polymer stuff that goes on too.
sounds good. What other questions or comments? All right. Thank you very much, everyone, for taking part in today's meeting. Very much appreciate all of you coming back month after month to join these meetings. I can see that we had one more person sign in, so I'm going to say hello to, let's see, Jorge Licia. Licia. All right. Welcome. And let's see, I saw Rich, Natalie, Sam, Doug, Bill Cleary, and Jorge. All right. Thank you very much, everyone. Look forward to seeing you guys next month. If you guys come up with anything specific that you really want to hear or know about our broad theme of materials, right? Or you have any particular experts who might be able to lend us a little more know-how or knowledge on that broad theme of materials, go ahead and feel free to send me an email. My email address is eric.kam at member.sme.org. Thank you very much, and until next month, I'll be talking to you guys. Be safe and stay warm.
Thank you, Eric.
Thank
Thanks,
you.
Eric. Bye.
Bye bye.